Hello again. We're back to continue talking about monitors and diagnosis. It's been a little bit more than a week, I think. In the meantime, face a little grubbier, hair's a little bit longer, stomach a little bit bigger, but otherwise doing well. I hope you guys are doing well too. Let me start by sharing the screen here with you and bringing up uh, Blackboard. So as you know, we have uh, our lessons we were under was called the slides for week 11. So this is what we were working on. Let me click on that, open it up. Just wanted to go through that so you remember how to get to what we're looking at. So we were on a slide called continuous self-test. That's where we last left off. If you want to look back through any of this stuff, then obviously you can just rewatch the old videos. So this is where we stopped. We had been talking about OBD1 sort of things, older stuff pre-96. And so now we're going to move on and talk about OBD2 additions. These are things that came along when OBD2 came along. So, all the tests that we had in OBD1 are carried over to OBD2. So all of the actual failure tests, uh, are still there, but then additional hardware and software were added for OBD2. So additional hardware such as, like a fuel tank pressure sensor, for example, to enable the evap monitor, uh, vent solenoid for that same thing. Uh, Oxygen sensors behind the catalytic converters were added to enable the catalyst monitor, etc. So biggest change, addition of monitors such as EGR monitor, catalyst monitor, evaporative emissions monitor, misfire monitor. And these monitors fall into two categories, or actually two major categories. So continuous and non-continuous. Continuous examples are misfire monitor, fuel system, the comprehensive component monitor, which is the same thing we had in OBD1. And these are just what they sound like. They run continuously. So whenever the car is running, these monitors are active. Then there are the non-continuous monitors, such as catalyst, O2 sensor, etc. These things may run, you go out and drive the car, they may run during that trip or during that drive. At some point, they may not if the conditions aren't met. And once they run, they don't typically run again. So they're not just constantly going. They run occasionally, let's put it that way. Not all cars have all monitors. So, for example, not all cars have an EGR valve or an air pump, secondary air system. So, obviously, they're not going to have those monitors. Talk about some more definitions here. Something in OBD2 called OBD2 trips and OBD2 drive cycles. So, what's a trip and what's a drive cycle? An OBD2 trip meets the conditions for a single monitor to run. So if we take, for example, the catalyst monitor, there's a set number of conditions, and we're going to talk about that a little bit later. Number of conditions that are required to be met before that catalyst monitor will run. So if I take my car out and I drive it and I meet all of the conditions for that particular monitor to run, the catalyst monitor, it will run. And we will say we have completed an OBD2 trip. If I take the car out and drive it and I meet the conditions for every single monitor, then we're going to call that an OBD2 drive cycle. The manufacturers have published OBD2 drive cycles. In other words, take the car, drive it, do these things, maybe idle it for a while, accelerate, steady cruise, decel, various conditions to try to hit the conditions for every monitor to run. So they have a definite OBD2 drive cycle that theoretically, if you take the car out and follow those directions, every monitor will complete. My experience with that has been mixed. Let's say mixed. For example, the evap monitor frequently requires a long cold soak or an overnight soak where the vehicle has to sit still for a period of time. You can't just force that to happen all the time. So, um, like I said, we'll talk about the individual ones a little bit. I have some documentation we can look at. Not all monitors require the same things before they'll run. So, for example, I just mentioned the EVAP monitor might require the vehicle to sit, where obviously that's not part of a catalyst monitor or a misfire monitor. If you have a Ford and you clear the diagnostic trouble codes, there's a special code in Fords called a P1000 that'll set. It doesn't indicate any kind of a problem. It just means the monitors have not all completed. Once you hit the entry conditions for every single one of those monitors and they all run and complete, the P1000 goes away. Now, if one of those monitors fails, you might get a different code, but you won't have the P1000 anymore. So here's an example of an OBD2 trip. Not any specific monitor we're talking about here, but it starts with ignition on. The PCM says, okay, what's the enable criteria for this monitor? And if we go down the right side, you know, if the enable criteria are not met, the monitor just plain old doesn't run. But going down the other side, right, if we meet the enable criteria, the PCM runs the test results are updated, and we shut down and we say we have successfully completed an OBD2 trip. Doesn't mean all the monitors ran, it means one particular monitor ran. Here's an example of an OBD2 drive cycle. Now this is just kind of generic. This is not taken out of any particular shop manual, but just to give you the idea, it says here that the total time for this is 12 minutes. So it gives you a list of actions to take along the bottom. So, for example, idle for 2.5 minutes with the AC and rear defrost on. It has to be a cold start, so the vehicle has to start out less than, engine coolant temperature has to start out less than, 50 degrees Celsius. Then, of course, we're accelerating to 55 miles per hour at half throttle with the AC off, then 3 minutes steady cruise, then decel, then accelerate again, cruise again, decel with no brake, and that's the end of the cycle. And theoretically, if you do that, it's going to take 12 minutes. And during that time, various monitors are going to complete. So here it's saying the catalyst monitor will have completed by the time you get to this point right here. Like I said, my results, mileage has varied on this sort of thing. So let's talk about individual monitors. And I'm going to show you some resources. If you're really interested in this stuff, you can go to those resources and you can look for yourself. But I don't want to get too deep into the swamp here. You don't have to design your own catalyst monitor. You just have to kind of understand how it works and what is required in order for that monitor to complete, and what a failure actually means. So a catalytic converter has this natural ability to store oxygen. And so the way that plays in during the catalyst monitor, if there's a period of time where the oxygen content in the exhaust is high, the catalytic converter will absorb that excess oxygen like a sponge. If there's a time when the oxygen content in the exhaust is low, the catalytic converter will release that oxygen like squeezing the sponge. So if you're looking at the oxygen content in the exhaust in front of the catalytic converter, it may be going excess oxygen, then a lack of oxygen, then excess oxygen. In other words, it's varying a lot. And because that catalytic converter stores excess oxygen and then releases it when there's not excess oxygen, it kind of has the effect of dampening, almost like a shock absorber, just kind of flattening out the oxygen level in the exhaust stream behind the catalytic converter. So a couple ways that this catalyst monitor can work. One, it can compare what's going on upstream to what's going on downstream. And if the oxygen levels are varying just as much downstream as they are upstream, then the catalytic converter is not doing anything. If, on the other hand, you have wildly fluctuating oxygen levels in front of the catalytic converter upstream, and then kind of steady or flat oxygen levels downstream, then something's happening in that catalytic converter. It's doing something. So that's one way that the catalytic converter is monitored is by comparing that upstream oxygen sensor to the downstream oxygen sensor. You've seen it in some of the labs. I've showed it on graphs, right? And what are they really looking at? They're looking at how frequently the oxygen sensor voltage switches from low to high or high to low. In other words, they call those switches every time it transitions across that 450 millivolt level. They call that a switch, whether it's going from low to high or high to low. The upstream oxygen sensor should switch a lot more frequently than the downstream oxygen sensor if the catalyst is doing anything. If they're very similar, then the catalyst is not functioning. They call that an index ratio, just a simple mathematical calculation. And then there's a threshold. If the index ratio is above a certain amount, then the thing fails. And if it's below that amount, then it passes. So that's one type of catalyst monitor. And another type, which is a little bit more active, is the computer intentionally drives the exhaust very, very lean. So on a D cell, fuel shut off, the idea is that catalytic converter is going to store a whole bunch of oxygen. And then, after it's been a long enough D cell with the fuel shut off to assume there's a lot of oxygen in the catalytic converter, the computer starts fueling again, and it looks, how much fuel do I have to dump into this thing before my downstream oxygen sensor indicates rich? If it indicates rich very quickly, that means the catalyst hadn't stored very much oxygen. If it indicates rich, if it takes a long time and a lot of fuel to drive it rich, that means there was a lot of oxygen in that catalytic converter. It's functioning well. So let me shrink this down a minute, and I'm going to bring up a resource that I think is pretty helpful. And this is a free one. So if you go to motorcraftservice.com, and this, it talks about Fords, obviously, but nobody's reinventing the wheel here. The catalyst monitor, the federal test procedure is not radically different from one manufacturer to another necessarily. So if you learn the way Ford does it, you're going to have a pretty good idea of how everyone else does it. So under free resources here, there's OBD2 theory and operation. And then it goes way back, let's see, goes way back into the 1996 model year, so when OBD2 first began. But I'm going to pick gasoline model year 2018. And that gives us information about how the onboard diagnostic system operates for gasoline engines in all the Ford vehicles in the 2018 model year. In fact, not just, I think it even mentioned, it doesn't mention diesel, but it measures heavy vehicles too that use gas. Let's see if I can make this a little bigger for you. That seemed to work. And there's a lot of information in here. It talks about individual monitors. It talks about, operation of flex fuel systems, which are ones that can run on anything from E10, 10% ethanol, right up to E85. Uh, and it can run on regular, uh, not, well, I'm sorry, E10 is regular. It talks about oxygen sensor monitors, EGR monitors, cooled EGR monitors, PCV system monitors, thermostat monitor, all kinds of monitors. And there's no way that we can cover, it just can't do it. Every single monitor that's available on every single engine that Ford put out in the 2018 model year, certainly, that's just one model year, we certainly can't cover everything that's ever been done from 96 to present. So I have to pick things that are relatively common, things that are out there on pretty much every car. There are a lot of gasoline direct injection vehicles out there. Uh, you know, there may be some some different things there too. So I just can't talk about every single thing. So we were talking about the catalyst monitor, and I was telling you, if I go back to my slides here, let me go back to my slides. Here is a picture of an oscilloscope screen. Now, because of the labs I've put out, you've actually seen screens that look like this, so hopefully you kind of understand that this squiggly line at the top is a voltage level that is varying, going higher, going lower. So one channel of our scope would be attached to the catalytic converter or the oxygen sensor in front of the catalytic converter. And then the other channel on the scope would be connected to the oxygen sensor that's after the cat. And if the catalyst is working, you're going to see, this varying voltage in front of the catalytic converter. And you're going to see kind of a flat line or not a whole lot of switches behind the catalytic converter. So, if you saw something like this, compare upstream and downstream, you'd say this is a good catalyst. On the other hand, if you saw this, which essentially indicates that nothing's going on in the catalyst, you would determine that catalytic converter was bad. This is really what the catalyst monitor, the software, is doing, what we just did there, looking at the front versus the rear and making sure they're not too similar. So back to that summary from Ford, and let me work my way down here. The catalyst efficiency monitor. Now this is right from right from the source, and we just can't read everything. It uses an oxygen sensor after the catalyst to infer the hydrocarbon efficiency based on oxygen storage capacity. High efficiency catalysts have sufficient or significant oxygen storage. This makes the switching frequency of the rear oxygen sensor very slow and reduces the amplitude, in other words, the height or the amount of voltage change, right? As catalyst efficiency deteriorates due to thermal and or chemical deterioration, its ability to store oxygen declines, and the post-catalyst oxygen sensor signal begins to switch more rapidly and with increasing amplitude. So the predominant failure mode for high mileage catalysts is chemical deterioration, not thermal deterioration. So it talks about several different methods. Index ratio method, using a switching oxygen sensor, which is kind of the old-fashioned type, and the index ratio method using a wide range oxygen sensor. We talked about these wideband sensors before. And then there's this integrated air fuel method, which I think is that's the last one I talked about, where it actually drives the catalyst, or drives the exhaust stream very lean, right? It says it integrates how much excess fuel is needed to drive the catalyst rich, starting from an oxygen saturated lean condition. So we're gonna put a whole bunch of oxygen into this catalytic converter, So it's oxygen saturated, and then we're going to see just how rich do we have to go. How much fuel do we have to throw at this thing to make that rear oxygen sensor read rich, thereby saying we've used up all the stored oxygen in the rear cat or in the cat. So we'll skip past, like I say, this, you can go to this website. There's no login and password. This is all free info. But I want to get to some of the things that, that you maybe want to know about uh, what makes this monitor run, when this monitor runs. Because sometimes you're driving the vehicle and you're trying to get these monitors to run to make sure that you've repaired a problem. Or in New York State, if a vehicle has to pass inspection, these monitors have to run. So just kind of scroll down. I know I'm skipping over a whole lot of stuff here. And what I want to talk about uh, is the, okay, kind of the logic that these monitors run by. All right, so here's a flow chart, a logic chart for a catalyst monitor using an index ratio. In other words, comparing the switching frequency of the front and rear oxygen sensors. So we'll start at the start. Always a good place to begin. And the first question, first decision box here, have the monitor entry conditions been met? If the answer is no, well, we go back around and we're going to loop like this for 100 years until the answer to this question is yes, right? So what are those entry conditions? Inferred catalyst temp. Now we talked about this with the last lab, right? Inferred means not measured. There's no temperature sensor in that catalyst, but inferred means we're pretty sure, that catalyst is hot enough based on other stuff. The fact that it's been, running for a certain period of time with a certain load on it, things like that. So is the catalyst hot enough? Vehicle and engine conditions. Is it a warm engine, steady drive? You saw back on this little drive cycle here, they wanted different conditions for different monitors to run. So if our entry conditions have been met, so here's the entry conditions, and there's actually a complete list of these I'll show you in a bit. And it's just all of these lists, and the amount of information available is huge. So I just can't sit here and read you a story, so I'm just trying to I guess lead you to water and show you where this stuff is, and try to hit the most important stuff. So if the monitor entry conditions have been met, then okay, we're going to accumulate the signal length of the front and rear sensors, count the sensor switches for each air mass cell, right? So here's what we're gathering: front and rear O2 sensor voltage, and we're looking at switching frequency. And first thing we want to know is, did we get enough switches in order to make a determination here? If the answer is no, all right, we go back and we just keep accumulating, right, until we do have enough. Once we have enough switches, we've counted enough switches, then we're going to divide the rear O2 signal length by the front to get the index ratio. Pretty simple mathematical calculation. Input the new index ratio into what? EWMA, what the heck is that? So that is exponentially weighted moving average. Don't ask, So we're going to calculate a new value, and if it's greater than the threshold, if the answer is yes to that, it's greater than the threshold, then the catalyst is deteriorated. If it's not greater, here's greater than sign, if it's not greater than the threshold, then the catalyst is okay, and that OBD2 trip, OBD2 trip is over. I don't care if you continue to drive the car for another 500 miles, the catalyst monitor has completed. So let's go back to the yes answer here, right? Catalyst is deteriorated. So what happens then? malfunction indicator light after 2 driving cycles above the threshold. So why 2 driving cycles? I think the fear is if we are too fast to turn on the light and set codes, we'll have false diagnostic trouble codes and false check engine lights. So this is a way where we really want to make sure that this catalytic converter is failed. So if it fails twice, and it's usually, consecutive, 2 times in a row, okay, it's probably actually bad. If it just fails once and then doesn't fail again, we're not turning the light on. There could be a few different reasons why the test didn't go that well. So we don't want false positives. Let's continue moving on down here. Here's the integrated air fuel catalyst monitor. So that's where we drive it lean intentionally and then see how much fuel it takes to make it rich. Same sort of idea, right? We start and, are the right conditions met? Same sort of thing, inferred catalyst temp. Got to make sure we have no hardware faults. Make sure the engine conditions are right. If not, back to the start until the answer to this is yes. Actually, the answer to this is yet. Then we wait for a deceleration fuel shutoff event. I'm driving down the road. Coming down a hill. I take my foot off the gas. As I think I've mentioned before, the injectors might be completely shut off. No fuel delivered at all. You don't need to make any power. You're in coast mode. So are the monitor entry conditions met? What are those conditions? Well, we got to make sure the injectors are off long enough and the purge flow is off long enough. So we don't want the canister purge solenoid taking fuel vapors from the canister and putting them into the engine. That could affect just how lean our exhaust is. It might not be as lean as we want. So we need a period of time where there's no purge flow and there's no fuel injection. The exhaust is going to go very lean. That should saturate the catalytic converter with oxygen. Once the catalytic converter is saturated with oxygen, okay, now the injectors begin fueling, and catalyst breakthrough, interesting term, but what this means is does our rear oxygen sensor, like how much fuel do we have to dump into this thing before we've used up all the stored oxygen in the catalytic converter and caused our rear oxygen sensor to switch from lean to rich. If it happens too quickly, too easily, that means our catalytic converter did not store very much oxygen and it's deteriorated. All right, so again, let's see, mil after 1 driving cycle for slow filter, 2 driving cycles for fast filter. I'm going to tell you, I don't honestly know what that means, but to me it means maybe it fails once, maybe it fails twice before we get a malfunction indicator light. So let's move on now to some more details about the operation. What are the diagnostic trouble codes that we can get for a failed catalyst monitor? We can get a P0420, which means bank 1, or if there's a wide pipe, in other words, there's only one rear oxygen sensor. Or a P0430 if we have a catalyst efficiency problem on bank 2. How often does this monitor execute? Once, and then it won't happen again until you park it and drive it again. What's the sequence? Well, first, the oxygen sensor response test has to be complete, right? We can't have some particular diagnostic trouble codes, if the secondary air pump is stuck on, if the EGR is stuck open, or if we have evap leak check DTCs, those are going to screw up our ability to maybe drive it lean, if we're operating too rich, if the air pump's on, these things are going to mess up. You're trying to measure the oxygen storage capacity of the catalytic converter. So what sensors have to be okay? A whole bunch of them. Okay, so if you have any of these diagnostic trouble codes, I'm not going to read through them all, right? But this monitor is just not going to run. So I have a Crown Vic that I think it was the one I used for the lab where we did the fuel injectors and all that. I can't get the catalyst monitor to run. I think it's the catalyst monitor. Um, it's got an evap problem. It's got like a hole in the filler neck or something like that, and it won't run the catalyst monitor. So sometimes you find things like this that happen, right? The the monitor can't meet the conditions because it doesn't know, if we got a bad coolant temperature sensor, well, if it needs a warm engine to run the monitor, but the temperature sensor's shot, then it never knows it has a warm engine. It's not going to run the monitor. So some of these other codes can keep monitors from running. How long does the monitor run? Oh, about 700 seconds during appropriate federal test procedure conditions. Needs about 100 to 200 oxygen sensor switches. Um, and if it's a wide range oxygen sensor, it only needs about 10 to 20 seconds. For the IAF catalyst monitor, right? That's the integrated air fuel catalyst monitor we talked about, where it floods the catalyst with oxygen and then sees how much fuel it takes to make it go rich again. It needs 3 D-cell fuel cutoff events. So you'll have to drive this and take your foot off the gas and let it coast down 3 different times before that monitor is going to run. So we have switching O2 sensor monitor entry conditions. We have wideband sensor monitor entry conditions. The integrated air fuel catalyst entry conditions. You can look at all these if you want, but let's just take the switching O2 sensor index ratio catalyst monitor. This is where it compares switches on the front O2 to switches on the rear O2. So these are the old-fashioned switching type oxygen sensors, not wideband ones. And I'm not asking you to memorize all this stuff, right? Just to get an idea. The engine has to be running at least 330 seconds before this monitor will run. The engine coolant temperature has to be somewhere between 170 and 230 degrees. Intake air temperature somewhere between 20 and 180. Has to have been in closed loop for at least 30 seconds. The inferred rear O2 sensor temperature, inferred, like I say, it's not measured, 900 degrees Fahrenheit, somewhere between 1 and 12% EGR flow. Part throttle, it has to be steady, right? So the rate of change of throttle position can be maximum, right? 0.2 of a volt in 0.05 seconds. Vehicle speed between 5 and 70. Fuel level at least 15%. And then a certain amount of air being measured, engine RPM, catalyst temperature, number of front O2 switches required. So all of these entry conditions, right? And so, there's separate entry conditions for wide range. There's separate entry conditions for the IAF. So what I mean by entry conditions is, what conditions have to be met before this monitor runs, going back to these flowchart things here, right? So entry conditions. If they're not met, we're dead in the water. We're not going any further and running it. So let's go back down now. Typical malfunction thresholds. So index ratio catalyst monitor for either bank, if the index ratio is greater than 3/4. If it's a wide pipe type, greater than 0.6. If we have a flex fuel vehicle, then it depends. If we're running on E10 and the ratio is greater than half, 0.5, that's bad. But if we're running on, E85, it's got to be zero point 0.9, greater than 0.9 for it to be bad. So, hopefully that's a pretty good kind of overview of the catalyst monitor. Unfortunately, what does it mean if the catalyst monitor fails? It means your catalyst is deteriorated. If you had a bad oxygen sensor, it would be a different code. You'd have oxygen sensor codes, and what would happen is, you would not meet the requirements, right? So uh, here's the HO2S response test. You can't have any of these codes for oxygen sensors. You would never meet the entry conditions, and so the catalyst monitor wouldn't fail, it just wouldn't run. You'd have to fix the other problems first. So if you actually get a catalyst monitor that runs and then fails, hate to tell you, but your catalytic converter needs to be replaced. So where did it say how many failures we need to turn on the light? I guess that was back up in these. So later we're going to talk about this, and I think I'll be using ALLDATA and a Chevy about types of diagnostic trouble codes. Some types set after one failure, some take multiple failures before it turns a light on. This particular one, right, the index ratio one, 2 driving cycles above the threshold. And we'll also talk about later, what does it take for that light to go out? So, if you have questions about these things, you can email them to me or you can call me. My phone's forwarded to my cell, so we can talk about it, if it's something you're interested in. Also, like I said, you go to motorcraftservice.com, and just click on this free resources. It'll bring you to this information. Misfire monitor, not going to get too much into. I mean, it's watching the crankshaft acceleration, and it's trying to determine if the crank is accelerating steadily. In other words, if each cylinder is pushing with the same amount of torque on that crankshaft. But here is something kind of interesting about it, right? There is a, let me find it, rough road detection. Now, I don't know if I go back to an older vehicle if I'm going to find this. This is a 2018. So because we're kind of looking for a nice steady rotation on that, crankshaft position sensor, apparently driving over a really rough road could give you a false failure on the misfire monitor. So they actually incorporate rough road detection into this monitor, right? And it uses data from ABS wheel speed sensors for estimating the severity of the rough road conditions. So it's to eliminate false misfire indications due to rough road conditions. If the rough road condition system fails, let's say you got bad wheel speed sensor or whatever, then that'll be ignored, and the misfire monitor will just work without any rough road detection. So that's pretty interesting, I thought. Well, let me bring this back up to full speed, full size. See if there's anything I kind of missed about any of these things. Catalyst monitor, right? I think I hit that pretty hard. So I'm going to pause us here. And I'll be back in a couple of minutes. Whether you'll be able to tell I left, I don't know. Okay, so I am just took a quick little break there. So I got a couple disclaimers about this slide and these numbers here. I make a few statements here, and I say at the bottom, if the long-term fuel trim exceeds 25% and the short-term exceeds 5, so a combined 30%, we get a lean malfunction. Well, I'm not willing to say that every Ford, um, has the same numbers, or every GM has the same numbers, or even as model years have gone on, I think if you go back to 1996 and look at the fuel system monitor on like an old, uh, you know, Chevy Cavalier or something, and then you go to a 2019 Honda, are you going to see the exact same stuff? Quite possibly not. I know the numbers I'm using were, I think, a GM one I had. It was a Cavalier. I'm pretty sure it was a student's car. We put that C recorder on it, and when I saw the check engine light come on and the code set, the let's see, where did I get this? See if I can find. No, I didn't put it in the slide, but it was some ridiculous number where I watched the fuel trim climbing, frame by frame as I stepped through the data, and it hit some kind of crazy. I think it was like 45% between the long and short term together, and then at that point, that's when it indicated the check engine light came on. That's a lot. I'm not willing to, bet the farm on those numbers. It's just what I saw. Uh, so, let's just talk about what's important here. The fuel trim, logic in the computer, its job is to try to keep the air fuel ratio at stoichiometry, even if little tiny things in the car go goofy, tiny little vacuum leak, things like that. Just wear and tear, the age of the vehicle. So it's just this little tweak meant to make minor adjustments in the amount of fuel delivered to keep the air fuel ratio where it belongs. So under normal operation, fuel trim numbers are very small. 2%, 5%, -3, single digits typically. In the event there's a larger vacuum leak or a problem with something else like fuel pressure or fuel injector flow or um, mass airflow sensor, not measuring properly, something that causes the amount of fuel to be incorrect by a lot, then the fuel trim numbers are going to be high. And every car has a limit to how high it's going to allow those numbers to get before it gives up and decides there's a problem. So, let's just kind of walk through this. I have a car sitting in the shop. The fuel trim numbers are small, 5% positive. I take a knife and I cut a vacuum hose or something. So all of a sudden now we have air coming into the engine, but it's not coming through the mass airflow sensor. So the computer doesn't know about it. All it knows is that, holy cow, we're suddenly too lean. Why? It doesn't know why. But okay, we're too lean. What's our job? Add a little fuel. Trim it. Add some fuel. So now all of a sudden we're at 10%. That's not enough. So we add more. Now we're at 15. We're at 20. What? At some point, The logic, the programming in the computer is going to say, wait a minute, I'm not adding any more fuel, something's wrong. And at that point, it's going to flag it as a problem. And that's going to be a fuel system monitor failure. Let me go back to the Ford OBD2 thing here from Motorcraft Service. And the fuel system monitor, I'm going to have to find it. EVAP monitor, I may have already gone past it. My apologies. I suppose I could go to the, no, that's EVAP. Probably go to the table of contents. The EVAP monitor, I'm sure you can see from all the stuff that I'm flipping through here, is probably the most complicated. Yep, still on EVAP, EVAP, EVAP. All EVAP. Purge, engine off natural vacuum. Here we go, fuel system monitor. So adaptive fuel strategy uses O2 sensors for fuel feedback, and the fuel equation includes short and long-term fuel trim modifiers. So, we take the air fuel mass times a short fuel and a long-term modifier and divide by the equivalence ratio times 14.64, okay, whatever. If we want it to be at stoichiometry, that this number is going to be 1. So we're going to be looking for 14.64. Greater than 1 is going to be lean, and less than 1 is going to be rich. Anyhow, so see if we have some standards down here for that fuel system monitor, things that are going to cause it to set a code. So, here's the monitor. Start, are the monitor entry conditions met? Are we in closed loop with warm oxygen sensors? Yes, okay. Continuously monitor short-term and long-term fuel trim. So this is not just once per OBD2 trip or drive cycle, it's continuously monitoring it. If the short-term plus the long-term fuel trim together are greater than the threshold, that seems a little crazy. I'm going to say that this should say less than the threshold, and it would be okay, and greater, it would be bad. And after 2 driving cycles with a malfunction, the check engine light's going to come on. So here's the question, what is the threshold? And that's what I'm telling you on this slide. I've seen it at 25%. I think I saw it at 45 on that Chevy. See what we got here. Possible diagnostic trouble codes are P0, 172, 171, 172, 174, 175. So we got bank 1 lean, bank 2 lean, 171, 174. Bank 1 rich, bank 2 rich, 172, 175. I have a feeling that's not correct. How long does it take to register a malfunction? Interesting. 2 seconds. What sensors have to be okay? Well, if it has a fuel rail pressure sensor, that's got to be functioning. We got to have good intake air temperature, cylinder head or engine coolant temperature sensor. Mass airflow sensor has to be okay, throttle position. So if any of those sensors are indicating a problem, this monitor can't run. Right? So you'll have codes for those instead. And it's a continuous monitor. Whenever you're in closed loop fuel control, it's going to be running. So what is our, here's the threshold. This is what I was looking for. All right. If the long-term fuel trim is greater than 25%, and the short-term fuel trim is greater than 1%. So that is a combined, fuel trim number of 26%. That is going to be a malfunction. Right? So as soon as it goes beyond 25, that's the bottom line. Now the way they wrote this is confusing because they're saying if the long-term fuel trim is less than 25% and the short-term fuel trim is less than 1%, it's rich. So um, that's wrong. Here's the way I think they should have written that, right? So what it should say, rich malfunction, right? Well, long-term fuel trim greater than negative 25%. Short-term fuel trim greater than negative 1%. Right? In other words, a lean malfunction, we're adding more than 25% fuel, and a rich malfunction is we're subtracting, right? Subtracting more than 25%. So I don't like the way they wrote that at all. Not good. But this is the number I was actually looking for. What is it on that Ford? So going back to my slide, right? Fuel system monitor. I guess, that's close, right? This really should say not 5% here. This should say 1. So we have a combined of 26. Anything over 25 is what the bottom line is. Now keep in mind, I'm showing you this is a 2018 Ford. You could look in a different year, you might find different numbers. I am not going to do that. I'm not going to sit here and go through every possible year and see what the exact numbers are. As a tech, you should just know that when you see a lean code, P0171, for example, then the problem is the computer has tried to compensate for a lean condition, and it has gone up to something like 25% positive fuel trim and still had a lean condition. So it's not going to just keep throwing fuel at it indefinitely. At some point, it gives up, realizes the problem is significant and needs repair, needs diagnosis and repair. So that's when you get your check engine light and your lean code. Let me do this. I don't like this right here. I'm not sure this is right. My memory is good, but it's short. So what I want to do is I want to go to all data and excuse me. Let me take the vehicle that I have been using, the 2010 Chevy. I think Impala with the 3.5. This is what I've been using. And under all diagnostic trouble codes here, right? And we'll get into these types later, but let me just go to P0171, all right? And this is not General Motors specific, right? These are SAE codes. In other words, every vehicle, if it gives a P0171 on a Ford, it means the same as it does on a Chevy or a Toyota. Okay. So Bank 1 lean 171, Bank 1 rich 172. I guess that does kind of match what we got. Bank 1 lean 171. Okay. My apologies. They were right. This is why I like to look things up. Don't rely on my memory. It's not good. Okay. See, do I have anything else? Malfunctions on 2 consecutive trips will eliminate the mill. Yeah, we're going to talk about how many trips, how many failures it takes to eliminate the mills for different kinds of diagnostic trouble codes. We're going to do that separately, so let's just drop that for now. Oxygen sensor monitor, is another continuous monitor, right? Continuously monitors switching of the oxygen sensors. if it's not switching or it's not switching frequently enough, it may flag an oxygen sensor code. Something we used to call a lazy O2, where the the voltage would vary enough, right? So it would go above and below that half a volt or that 455 millivolt number, but uh, it would do it really slowly. And sometimes, oxygen sensors that are contaminated, if there's things in the exhaust, let's say the engine's burning oil or the engine is ingesting coolant. Now this comes out in the exhaust and coats the tip of the oxygen sensor with contamination, and the oxygen it's not in good contact with the sensor tip. uh, you can have problems that way where there's nothing electrically wrong with the sensor, but it's just physically coated with garbage. Another thing they do here, if it's over 1.1 volt for more than 30 seconds, fails the over voltage test. So again, we could go back to the Ford, the Motorcraft service thing here, and look up oxygen sensor monitor, and I'm sure it would tell us the exact, criteria for that. But I don't want to get into trying to do that for every vehicle, every year, every monitor. Another thing, another way that the oxygen sensors can be tested, and this rear O2 gets tested this way too, right, is um, so the computer is in charge of the fuel injectors. It's in charge, it has the ability to intentionally lean the engine out or richen it. And so if you wanted to test an oxygen sensor's ability to pick up rich and lean conditions, what you could do if you were the computer is say, all right, I'm going to intentionally drive it lean, and I should see a low number from that sensor. And then when I intentionally drive it rich, throw more fuel at it, I should see high numbers from that oxygen sensor. My sensor should respond to the actions I take. If I throw more fuel at the engine, I expect that sensor to show rich. If I take fuel away, I expect it to show lean. So I can, dynamically test the ability of that oxygen sensor to respond or to measure what I'm doing on the input side of things. All right, I'm not going to get into the EVAP monitor yet. I think we'll stop right here because the EVAP monitor is probably the most complicated, and I think we're far enough in. We've spent enough time today that I think I'll call it a day. And by the time you've watched this, I should have questions posted on Blackboard, a little quiz, so that after you watch this video, you can take that quiz. Some of you are missing some quizzes. I think, if you don't know that you have taken all the tests and quizzes that have been out there, for every video there's a quiz. So if you've watched a video and haven't taken the quiz, or if you haven't watched all of the videos, this is lecture number 4, so this will be the 4th quiz. Each one is 10 questions. If you haven't done that, you better get a hold of me, because this is how your final grade is going to wind up being calculated this semester, is based on that first test and the quizzes we've been doing on this. So definitely get a hold of me. Some of you have done that. I have allowed you to take them late. Some of you have some, extraordinary situations at home. I know one of you has 5 kids, a full-time job, and is a full-time student. You know who I'm talking about. We've had conversations. Happy to help you out if you're trying. If you're just blowing things off, well then, I guess I won't be hearing from you. So, watch this, take the quiz. I think at most there's going to be one more. We're running out of semester. So good luck with it. Hopefully this helped. Hopefully this gave you a little bit better understanding about some of the stuff you'll deal with in the shop on a day-to-day basis. If not, like I say, email me, call if you have questions. Again, just to make sure you know what those resources are that I was using. ALLDATA, you have access to this at least through the end of the semester from home. And, you know, this information, which is Ford specific, but a lot of OBD2 stuff is, you know, mandated and standard, you know, throughout all car manufacturers. So the information in here that's good for Fords, a lot of it is good for Chevys or Toyotas or Hondas or Suzuki's or well, Suzuki's, Subarus. Uh, so it's good to look through. It's motorcraftservice.com, you know, and then under free resources, um, OBD2 theory and operation, and then you can pick, you know, the various years. I am operating in gasoline model year 2018, like I said. So good luck with the quiz, and I'll see you in the next video.